Hello, everyone. Um, it's my pleasure to be here to help to present this paper, MetaGen, an LLM-driven generative framework for intelligent metasurface algorithm design, developed through collaborative research between Tsinghua University and Northwestern Polytechnical University. In this presentation, I will systematically guide you through the MetaGen's research motivation, the key challenges, and innovative solutions, comprehensive evaluation results, and the framework's significant contribution to the intelligent metasurface algorithm design powered by large language model. Let's first establish the fundamental concept and the practical application of the metasurface. This artificial electromagnetic surface poses the remarkable capability to manipulate waves at sub-wavelength scale. Their distinctive advantage including exceptional power efficiency, dynamic programmability, and cost effectiveness. Position them as a revolutionary components for communication system, sensing technologies, and security applications. However, conventional design methodology heavily depends on the specialized expertise and repetitive simulation cycles, resulting in processes that are both time-intensive and inherently inflexible. Recent advancement has attempted to automate metasurface design through neural network components, incorporating generative adversarial network, variational autoencoders, and diffusion models. Yet significant challenges persist. GN exhibits instability during training convergence. VAE tends to generate indistinct pattern output, and diffusion model demands extensive complex input specifications. Our design objective focuses on developing a comprehensive, efficient, and intuitive accessible solution for metasurface element generation under diverse design constraints. The innovation workflow empowers users to articulate their design requirement naturally in everyday language. MetaGen intelligently guides them through the requirement refinement, generate preliminary designs, and seamlessly accommodate design modifications through iterative reprocessing to deliver the updated results. To realize this vision, we present MetaGen, an integrated framework that revolutionizes metasurface design through three synergistic modules. The core innovation lies in the leveraging large language model for intuitive user interactions, employing advanced generative model for structural synthesis, and implementing an intelligent selection mechanism to identify optimal design from generated candidates. While the conceptual foundation appears straightforward, we encounter several critical implementation challenges. The primary obstacle involve frequency and structural generalization. Electromagnetic response demonstrates extreme sensitivity to frequency variation and geometric configurations, creating substantial difficulty in achieving robust generalization across diverse scenarios. Addressing the generalization challenge requires significant enhancement of our open source dataset, originally collected through needle drop methodologies. The initial dataset presented multiple limitations, including restricted parameter variation and cross-frequency sampling, frequency sampling intervals of 0.1 terahertz. Our comprehensive enhancements expanded parameter coverage, incorporated additional substrate material, and implemented fine-grained frequency sampling. These improvements enable the model to effectively capture complex nonlinear relationship between geometric configuration and electromagnetic properties. A secondary challenge involves reducing the technical barrier for non-specialist users. Traditional approach requires users to provide detailed electromagnetic response data, which is a substantial obstacle for those lacking metasurface expertise. Bridging this accessibility gap requires establishing an intuitive connection between natural languages and expression and physical property. Our solution implements a transformation process where the large language model extracts critical design parameter from user input and generates corresponding formatted electromagnetic response specification for subsequent processing. To ensure alignment between the LLM's output distribution and the generation module training parameter, we synthesized a specialized user LLM dialog dataset using GPT-4, followed by supervised fine-tuning of our interaction module's language model. The final implementation challenge centered on achieving both high-quality element pattern generation and computational efficiency. Given a structured design requirements, the Metasurface design problem translates to a condition generation task. Our solution implements a diffusion-based generative model architecture. The current virtualization illustrates our generation module's training and inference process. During training, the forward process systematically introduces noise to the structural pattern, while a conditional unit learns to predict noise based on electromagnetic response and design parameters. The generation phase initiate from Gaussian noise and progressively refines outputs through iterative denoising. By embedding conditional parameter at each unit layer, we maintain critical design information while enhancing output quality. Our evaluation module further enhances system performance by predicting electromagnetic response for generated design and selecting optimal candidates through batch processing. To maximize prediction accuracy, we implement an ensemble learning strategy. First, bootstrap sampling creates diverse training subsets, enable the training of multiple CNN-based prediction models. This model outputs are then aggregated through our averaging to produce robust final prediction. As our result demonstrates, this approach achieves substantial error reduction compared to single model implementation. Proceeding to our evaluation finding, we first examined MetaGen's overall performance. This slide showcases our implementation user interface. The interface accepts natural language inputs. MetaGen iteratively guides the user through requirement refinement before generating both structural design and corresponding parameters. The integrated display panel simultaneously presents electromagnetic response curves and generated design visualizations. For comprehensive end-to-end evaluation, we test MetaGen on two benchmark datasets: our enhanced MetaEM dataset and the established free-form dataset from previous research. We define success criteria. The operating frequency needs to fall within the user-specified bandwidth, with an additional succeed with tolerance matrix, allowing minor frequency deviations. The comparative results clearly demonstrate MetaGen's superior performance in Metasurface element generation across all evaluation metrics. We conducted detailed component-level evaluation of MetaGen's three core modules. The system's critical innovation lies in its ability to transform imprecise user input into accurate physical parameters. To validate this capability, we compare our fine-tuned LLM against the base model. The presented table quantifies a success rate in converting natural language input and to electromagnetic response across multiple tolerance levels. The results conclusively shows that through a LoRa-based fine-tuning, we successfully aligned LLM's output with the generation module's training distribution, effectively bridging the gap between intuitive user expression and precise physical specifications. The generation module demonstrates exceptional capability in frequency generalization, multi-band design support, and structural flexibility. Represents several representative examples highlighting this strength. First, we evaluated performance across both training frequency band and the previous unseen frequencies. As visualized here, generative structure maintain excellent EM response matching even outside the training frequency range. Second, MetaGen successfully handled complex multi-band design. When challenged with a triple band structure requirement, it produced a geometric configuration with precise residence at all target frequency. Each remains within specified bandwidth tolerance. This outcome confirmed that MetaGen effectively captured the intricate nonlinear relationship between geometry pattern and electromagnetic property, enabling reliable generalization beyond the training domain. Furthermore, MetaGen exhibits remarkable structural agility, generating differently sized elements for identical frequency requirements. This example demonstrated two distinct element sizes producing nearly identical electromagnetic response through intelligently varied pattern, validating the system's structural adaptation capability. Collectively, these three examples provide compelling evidence of MetaGen's robust generalization across diverse operation conditions. We perform a rigorous comparative analysis against two established baseline models, CVAE and WGA-GP. The results include both quantitative and quantitative assessment. The left visualization contrasts MetaGen's well-structured output with the irregular pattern characteristic of JN and VAE approaches, while the right figure demonstrates that MetaGen's generated pattern achieved the closest electromagnetic response aligned with the target specifications. For deeper analysis, we conduct comprehensive quantitative evaluation using 5 distinct metrics, assessing design target matching precision. The comparative table reveals that MetaGen's superior performance across all evaluation criteria. The accompanying figure illustrates relative performance changes with transition into unseen frequency band, clearly indicating MetaGen's exceptional frequency generalization capabilities. Finally, we validate the evaluation modules in ensemble learning implementation. Without bagging, prediction error exhibit wider variability. The bagging implementation produced a significantly tighter error distribution. This empirical evidence demonstrates how our bagging algorithm enhances the base model's prediction reliability. This improved consistency ensures users can confidently rely on the module's real-time feedback, eliminating the need for computational expensive HFSS simulation for every candidate design. In conclusion, MetaGen represents a transformative advancement in Metasurface design, delivering a general-purpose, efficient, and accessible framework for element generation. Our solution demonstrates Metasurface design for non-specialists while supporting complex multi-scenario application and demonstrating unprecedented generalization across optional frequency and structural configurations. Thank you for your kind attention. For complete technical detail, please refer to our published paper.
guessing the author is not here and you won't be answering questions, is that right? Okay, so unfortunately we don't have anybody to answer our questions, so please reach out to the authors if you have any question. We're gonna move on to